Right, so let's start. Good morning, everyone, and thanks, Anatael, for coming. So we are pleased today to welcome Anatael Cabrera to a seminar about an innovative project for neutrino detection. Anatael did his PhD at Oxford in 2005 and has been a staff scientist at the French National Center for Scientific Research since 2007, after a 3-year Marie Curie fellowship grant. Anatael's expertise spans neutrino science, detection and instrumentation hardware, namely on optical readout, electronics and scintillation systems. At CNRS, he has led innovative projects in these fields and founded several international consortia. Examples are the Super Choose Pathfinder since 2022, the Cloud AntiMatterOTech since 2023-21, the Double Choose since 2017, and LiquidO since 2016, which is a novel technology for fast detection and identification of particles down to a fraction of MeV.
Sorry.
So, today Anatael will tell us about this technology, the novel scientific opportunities it brings to neutrino physics, and the related projects for industry innovation in medical and nuclear applications.
Thank you.
Thank you.
Thank you very much, Wendy. So thank you very much for the invitation. So this time I think I'm going to tell you more about LiquidO, but I'm going to have a little bit of a pinch of a few other projects. Especially one project that actually is bringing me here is that we're bringing a lot of what we are going to hear possibly to Lisbon, to IST, and we're starting a strong discussion with LEAP essentially for possible collaboration. So let me tell you about first LiquidO. And I thought about introducing why LiquidO in many ways. I mean, is this yet another technology out there? And what I wanted to basically motivate, essentially, we're motivated by the context, kind of the big physics that we're here for. In a way, we're motivated by the fact that the standard model, we don't see the map. The batteries are kind of, I don't know if I let you, because it does. Thank you very much. Oh, let me get my timing. And so the goal actually is to address, to look deeper into the standard model. In fact, it turns out actually we are in this, I'm not sure it's beautiful or unpleasant situation. In many ways it's both, because the standard model is an absolute success. It is able to predict almost everything that we're testing out there, but it still is a mystery at the same time because we know it's incomplete. We know there are certain things that actually standard model cannot even basically get nearby. Like the asymmetry of matter, antimatter in the universe, in many ways, why we're here. So we know that the standard model cannot explain why we're here. Still, it's able to predict virtually everything which we're measuring out there. And worse, in many ways, especially for particle physicists ourselves, we have no hint of the new physics out there. And therefore, the big thing is how do we get there? And the answer there, and these days, I'm not original on that. Oh, thank you very much. This is what we have been doing, since ever. Essentially is to get better and better and better experiments, essentially, to be able to see what's going on. So a little bit long story short, the panorama today, we have LHC in Europe, something that we're very, very lucky for. As a matter of fact, we become in many ways, the center of high energy physics in the world. And, but virtually all the other big laboratories right now, basically in scope, they are kind of leaning neutrinos. I wouldn't say they're fully shifting to the neutrino, but it's kind of ironic, actually. It's kind of basically telling us that something very big is actually happening in neutrinos. And indeed, there are 3 big things happening in neutrinos. There is the Dune experiment in the United States being built. Juno actually is already, it's about to basically be finished, the construction. Actually working in June, in fact. Hyper K in Japan, that is basically the bigger version of Super K. And right now, as we speak of, we are basically going through billions, not millions, billions of euros of excavation to make these experiments happen. And they're going to happen very, very soon. As a matter of fact, Juno should be taking data within a couple of years' time, worst case scenario. And we're going to address some questions. And now fundamental questions. You would argue these are the fundamental questions. Well, Not really. These are very important fundamental questions, but these are the fundamental questions we can achieve with this technology. The reality is that there are some fundamental questions that we would love to achieve. The reality is that we don't have the technology to get there. And I'm going to try to highlight that a little bit to motivate why we're trying to do LiquidO. So this is a little bit more of a Photoshop, basically a photo scenario. So this is Juno. This is basically a liquid scintillator detector being built in China, very close to Hong Kong. Actually, I participated, on some of the elements, the hardware elements of that. And in fact, this detector is almost super chemicandide made of liquid scintillator. Roughly speaking, this is where it comes down. Then there is the SURF, basically underground laboratory in the States, where it's going to be hosted basically June. So this is actually the latest pictures coming out from there. And actually, Fermilab, now they call themselves the neutrino capital. I'm not kidding, actually, this is in the website. So actually, Fermilab is basically pushing very heavily neutrinos, and this is absolutely clearly their goal. And hyperchemicandide is being built as we speak. You can see the size. The dome is basically up here, and this is the status of hyperchemicandide, probably some month ago, as a matter of fact. And what they want to basically build is a 10 times bigger superchemicandide, long story short. This beautiful, stunning detector that you can even take a little bit of a sail inside. So now, I thought of basically highlighting basically why LiquidO in many ways. Well, the first thing, if you look at reactor neutrinos, if you look at the neutrinos, well, we cannot do more reactor neutrinos not because there is no reactors out there. We cannot do it because we are dominated by the background. We're dominated by technology, long story short. I remind this was Nobel Prize. This was how neutrinos were discovered. There is solar neutrinos, also Nobel Prize. This is how neutrino installations were discovered. We're dominated by technology. Boraxino has demonstrated that it's almost impossible to go any farther. But we are still, the error bar is very, very large compared to actually basically what astrophysics we were supposed to basically be doing. Getting there? Well, thank you very much. And atmospheric neutrinos, another Nobel Prize, as a matter of fact. This is basically, again, how neutrino oscillations were discovered. Again, dominated by backgrounds and dominated by technology. Long story short, nobody knows how to basically solve it. That's the problem, but that's backgrounds basically are telling you that it's not the flux, it's not the cross-section, it's actually basically a technology. Supernova, another Nobel Prize, as a matter of fact. This is also dominated by backgrounds and technology. There is accelerators. So far, we have been dominated by the flux of the accelerators, but very soon, as soon as, for example, Dune and Hyper-K come along, systematics are going to be dominated, and this suggests technology, detectors. Again, Dune neutrinos were discovered in 2004 by Camland and follow up basically by Boraxino. This is dominated again by technology. And double beta decay, nobody have seen it, unobserved, dominated by basically background technology, and proton decay, essentially these are basically also dominated by technology, and clearly I would argue, I'm not sure what will happen with these two, which is beautiful physics, but these two, for sure, these are potential Nobel Prizes basically cases, and as you can see, the picture is very clear. We are dominated almost everywhere by technology. So the question, can we go farther? And LiquidO is just maybe one step in this direction, certainly not the last, but hopefully one of the good ones, and hopefully inspiring other people to go even beyond, and clearly we need to push on the technology level. And this is what, pushed me personally for LiquidO. There is another reason that I want to get for LiquidO is to try to eliminate our need for the overburden. You would see that all these detectors basically implies billions of euros of excavations. What if instead of putting money on making holes, you put it on the better detectors? Well, unfortunately, we don't know how to make those detectors. That would be beautiful, but unfortunately, we don't know how to do it. So a lot of the money, actually half of the money, roughly speaking, goes into the holes and not on the detector. And the question is that the best way to do physics? And so far, yes, because we don't know how to do it. As a matter of fact, better than that. But the big thing is, can we start basically getting away from this limitation? So can we make detectors, and this is from the artificial intelligence makeup, essentially, can we make in the future big detectors essentially in the surface? And the answer is yes, if anybody knows how to handle cosmogenics, that's it. Sounds very simple, but that has not been done over about 70 years that we've been doing neutrino physics since the discovery. So we have this absolutely stunning, beautiful technology. And let's face it, this is so beautiful that it's hard to give up on this, and we don't want to give up on that, but the reality is that that beauty is to a large extent the limitation that we're suffering from. Detectors being transparent, so what we thought it was the absolute fundamental feature, the reason of being, almost the ichigo, as the Japanese would say it, essentially is the main limitation that we have for that, and I'm going to highlight that. And to a large extent, essentially, trying to basically get detectors with less shielding and even less overburden is one of the name of the games for LiquidO. And we at least going to try Let's see how far we can go. That doesn't mean that basically this is not I'm not a politician, so I cannot promise it all. But I mean, at least I'm trying, we're trying to push in this direction, and hopefully this is something that inspires others. LiquidO. So with LiquidO, what we want to do is go back to the basics of basically making pictures. This is basically the first picture in the world, in France, in Paris, in fact. And the art of basically making pictures at the time, they were not even called photography at the time, is to make points in 2D. So it's about basically making something that has more light or less light, basically has a point, essentially, and we place them at least in 2 dimensions. Forget about 3. 2 dimensions, this is as far as we go. At the time, we used basically molecules with silver, and this is the famous. Now we use pixels, these are the CCDs. But long story short, this is exactly, and there's been a big revolution on that. But long story short, what I want to say is that putting points in space is already the beginnings of imaging. And that's exactly what we're going to try to do with LiquidO. The building blocks is we want to basically have, whenever you have each energy deposition, we want to place basically these energy depositions in space, 3-dimensional space, and we want that these energy depositions, that this little point in space is actually proportional to the energy. That would be beautiful. If you have more energy, it's a bigger point. If you have less energy, it's a smaller point. So this is like when you do root and you put basically energy deposition in space. If you actually you're able to make little points. If you make a sequence of points, you make a line. So you have now tracks, okay? So you can go into a complex. And then you can organize them in time. If you have the time in resolution, it turns out our detectors are very good when it comes to time. So that's not a worry. Actually, it's much easier to do time sometimes than good charge. And if you actually put all this information together, you may see how these events are evolving, and we call that energy flow, okay? This is the wish list. Let's see whether we can make it. And this is actually what inspires to a large extent, essentially liquid in many ways. Can we make these kind of things, kind of the things that we imagine in our eyes, but not what we see in our detectors? Can we make it happen? Well, the challenge is that now we want to use light detectors, okay? And we don't know how to confine light in space. Well, actually we do. This is what black holes do, but we don't know how to make detectors with black holes. Unfortunately, I don't know how to do that. But we may know how to do that, actually, instead of basically using black holes, gravitation, we may basically give up on transparency, where photons, this is Gen 4, behave like rays. They go to the infinity until they are absorbed, essentially. So this is our paradigm of detectors. Detectors are beautifully impeccable. And we may move to the Milky approach, where now the photons actually going to stay local. They're going to revolve. It's random walk. This is, as old as everything in many ways. And the photons, instead of behaving like a ray to the infinity, they're going to behave more like a random walk. And it's going to define basically a point. Because on average, a random walk says that the average displacement is 0. It stays basically close to the original point. And if you have one photon, that's what happens to one photon. If you have many photons, this is what it would happen. And you would make a little light ball. And this means you have now your basically primitive point in space, which is proportional to energy and is proportional to give you the time. So we succeeded there. And the ironic thing is that instead of basically going into this paradigm of transparency, we went exactly the opposite way. We went into opacity. As a matter of fact, this is because O of opacity, this is what LiquidO. Of course, you don't want to absorb the light. Opacity means can be done through absorption. That's bad, you lose the photons, okay? But you can do it also through scattering, and now you keep the information locally. Instead of washing the information away, like a streamer, okay? This is a typical famous feature of neutrinos, for example, in supernovas. We actually keep the neutrinos locally. As a matter of fact, they behave like that in stars. We do that for free using Mie scattering and Rayleigh scattering. As a matter of fact, what we've been doing for all the time is avoiding it, but that is actually for free in nature, as a matter of fact. This is actually the easy stuff. Transparent detectors is the difficult thing. As a matter of fact, people have to spend an immense amount of money to get there, while actually getting a detector that do that is so simple as milk, as a matter of fact, because that's an emulsion. And this is scattering, basically the photons are scattering in the fat of the milk. Mayonnaise is the other way around. So, long story short, we want to go away from that has been our absolute core of our detection to that. This is a fiber, this is full Gen 4, and we want to go there, and instead of basically avoiding scattering, we're going to maximize it. We can tune it. We can tune it in a way that the fibers are just sampling the sizes of the light balls, and actually they're part of the detection, as a matter of fact. So instead of basically what we want to achieve is that a positron, and a positron here is a positron is manifesting here, And then there is the annihilation, and you can see this point with wings, if you like, you can call it an angel if you may want to call it that way. That is actually a positron, and that's annihilation. And you can tell if it was an electron, there would be no annihilation, that would be just a single point, because from electromagnetism, electrons and positrons behave the same, except that positrons annihilate as opposed to electrons. So if you're able to see this pattern, now you can tell the difference between an electron and a positron, and that's major. And if it was a gamma, you would see what it looks, but it would look different. Now, if you do an opaque medium, you clarify things. It's kind of, this is where liquid is totally twisting your mind. Actually, this is opaque. This is like when you take off your glasses. You see better by taking off your glasses as opposed to actually transparency where everything washes out. And this is because the photons want to go to the infinity and they just washed everything out. So long story short, and this is where liquid is a crack, it makes no sense, but it makes sense. It kind of makes no sense at the very beginning. And I admit it, it took a while. Good, let's build an image of LiquidO. So imagine we go back to this positron. These are just energy deposition. This is basically the annihilation happened here. Quantum, and at the end of the day, photoelectric effect. And we actually transform every energy deposition in GN4 into a light ball. And this light ball is read out by fibers crossing the detector. And we have two carbon copy images, one another, modulo Poisson statistics, and actually some little propagation of photons, but you have basically two images. If you have some noise, it turns out to be noise here is different from there because it's silicon PMs and so on. Everything that is correlated is the real image, and you can clean the noise very easily. And as a matter of fact, this is exactly what we try to do. And if you actually use the timing, if you have very good timing though, very good timing, you can do a TPC-like, where you don't need basically a start signal and a stop signal in a way. It's not like a TPC. You actually use the time difference as a matter of fact. This is tough, because you can get resolutions here on a few nanoseconds, but nonetheless it's actually relatively very good. But you can do that. So you can actually get three-dimension images on that. This assumes these vertical slice. This is vertical basically fibers. I call it the 1D lattice approach, but we can do something more funky than that. So this is where now how images would look. This is in nanoseconds. You get the positron is ignited in the center, and this is opening in the both directions because this is annihilating. This is coming from the center. This will be an electron-like, and clearly this is not going to be an electron-like. So all the electron-like backgrounds in a positron signal, they're going to be largely eliminated. A positron signal is an anti-neutrino in a reactor because a reactor is an antimatter generator from the neutrino point of view. Right. And it turns out that if you actually do the same simulation with transparency without opacity, you see that you don't see. As a matter of fact, transparency, again, is not our friend in this kind of basically framework. The reason why you see some scattering here is because the fibers are scattering and the fibers are collecting the photons. If there was no fiber, you would see even not that. You would see something even worse than that, as a matter of fact. So that is already a fantastic detector because you can see a little deposition here that tells you that that is not supposed to be essentially an electron-like. Now you can go funky. You can assume basically these fibers in this direction. You can work out Z using timing. This is fragile. You have time walks. You have little effects here and there. I'm not going to go into the details. Of course, you can put fibers in the opposite direction. This is no problem. This just costs you money and a lot of engineers basically working on that. You can even put 3 axes if you wanted to because you want to go something very funky. You want redundancy. In some cases it's very important. But this gets very complicated. But you can do something different, which is basically crossing the fibers. Because now with the fibers, you can do amazing things. Amazing things, and I really mean it, amazing things. And you can cross fibers, and this implies that your resolution in Z that was not that good, now is taking some information from X and Y that was beautiful on a millimeter, sub-millimeter level, and now you can get basically to the centimeter level. This means that this detector is 1 or 2 or even 3 orders of magnitude better in resolution in vertex. This, you may say, oh, why does it buy you? Well, if you have a coincidence, one event and another event nearby, well, now you improve your background resolution. If you have 2 orders of magnitude basically better in 1 dimension, this goes basically to the 3rd power of that. So this means a factor of 1 in a million rejection if you're using coincidence. And it turns out reactor neutrinos, we use coincidences, and also some neutrinos, the solar neutrinos, can use coincidences. And this is something I'm going to mention later on. There you go. Technologically, we need fibers. We need these wave-shifting fibers. We can actually measure scintillating and Cherenkov light. We need a new technology on scintillator. I would come into this. We need fast readout with silicon PMs. And we need waveform digitizer, although this is arguably not totally needed, but this is the power you can do. You can reconstruct every single P, and you can actually identify to the picosecond level every single P. And this is basically something we've done in data too. Right, so this gives you, actually, LiquidO is not a specific detector in a specific, basically, way. LiquidO is a framework, is a new way of thinking about things, and it depends on your physics. You may customize it one way or another. So here's the most difficult part of my talk. I'm gonna try to tell you LiquidO in a generic matter, and you're gonna be thinking probably of your physics, and you're gonna be thinking maybe, oh, my physics may not be that way. My apology, I would basically try to address that later on. I'm gonna try to explain the technology, and let's see basically how well that could go basically to your physics, and it may well be that it doesn't work out. C'est la vie, eh? Now, very important, fibers are fundamental because the fibers are going to be used to collect the light, to pick up the light. They are also scattering elements, so the fibers are a critical element, and you need wave-shifting fibers or scintillating fibers. Many ways, it doesn't matter to a large extent. This is a cheap version of that fiber, long story short. This is basically a bad scintillating fiber that actually scintillates very little, and this is a much more high-yield scintillating fiber. But what is clear is a clear fiber is rather useless because it doesn't pick the light. It doesn't collect the light inside, long story short. So the fibers are used for two purposes: to collect the light, essentially, towards the readout, and the other very important, you would see that there would be some funky things that you can do with that. Right, now, let me go now to the scintillation. So as we have, breaking, I'm having a little logistical problem here, there you go. Okay, so when we have an energy deposition in a scintillator, typically we produce energy is going to a solvent. Actually, this is the part that typically doesn't scintillate. People normally call this a scintillator, but that's actually the solvent. And there is a very funky quantum mechanics basically behavior that this, which is a huge amount of the volume, this is a little amount, just 1% or less. As a matter of fact, is a quantum mechanical behavior that is called a FRET, essentially. So it's a resonance energy transfer, long story short, that we are transferring energy from the solvent into that. Even though the concentration of that is even on the per mil level, most of the energy manifests like if it was collected by that. It's like a turbo in a way. And this is just the power of quantum mechanics. So in fact, scintillators are already using quantum mechanics in a lot of ways. Then you can put photosensors, photomultipliers of silicon PMs, and this is a perfectly valid basically detector. In fact, this was a snow class at the very beginnings, as a matter of fact, using only PPO. But then you can actually do something else, which is actually using a second scintillator. So this is now radiative. This is no quantum mechanics anymore. This is a photon from here is exciting that basically part and sending it to the scintillator. It's slightly better shifted, so it's less absorption. And this is typically, you get even more for a bigger detector. In fact, that's a snow class as today, as a matter of fact. So what we actually do to make LiquidO, long story short, we actually substitute this second scintillator by the fibers. That's it. And it works. It's a piece of cake. Long story short, from the technological scintillator point of view, it's already basically working. In fact, these are the first scintillators that we built in France, essentially by 2018, actually, I think it was 2016 or thereabout. And in fact, we started basically saying that opaque scintillation was actually useful. Let me tell you something very straight on that. Anybody that did that before LiquidO, we call it a crappy scintillator. This is rubbish. This is useless. Why? Because the PMTs would not see. It was not transparent, and many people did that. In fact, I've done it because I'm so bad with scintillators that I did that a couple of times. But this is actually what it was basically, and I want to emphasize this, things that we used to trash, things that we used to think it was useless in many ways because it was not good for photomultipliers, for transparency, they can be revised now, they can be reconsidered. This means also that a lot of the materials that we use in today's scintillators, they are there because they are transparent. Scintillation is actually rather common in nature, but transparent is not. Ironically, transparency is actually very not common, as a matter of fact. So if you actually go back to your books of scintillation, you would discover that there is amazing scintillators that are not transparent. And that's exactly what we're now looking at. So what we have been doing so far is opacifying transparent technology. But what we want to do, as a matter of fact, is creating new opaque native scintillation technology. And that is actually opaque scintillation. And to be honest, this brought me to Lisbon, because in IST you have a chemical department with a couple of very funky people that do these kind of things. And that's actually what brought me to Lisbon. And that was the beginning, I hope, of a long, long, long story. And in fact, this is why I'm here. Let me continue the story now. This is our second scintillator done in Max Planck, and this was actually putting wax. So this was basically making a candle. So you just basically, with temperature, when it's warmer, it gets transparent and it actually basically is liquid. Like if you look at, close to the candle, look at the flame, that's exactly how you see a candle. This is with wax. So this means with using temperature, we can basically change the opacity. Opacifying potentially scintillators is a safety basically treatment in a nuclear reactor. This is also very interesting. So you see how this derives, this opens, and I'm not saying that we're going to use that in a certain experiment, but you can see that maybe in your experiment, in your context, you may start saying, oh damn it, that's exactly what I've been dreaming all my life. There you go. But there is something else you can do. You don't see it. This is actually milk. You can actually make emulsions. So emulsions is milk is water with a little bit of fat, 3, 4, 5, that depends on how much fat you bring to the milk, up to 5% of fat. And the photons scatter, this is why it's white, it's mean scattering. Mayonnaise is white because the same behavior, but the other way around, as a matter of fact. You have oil and you put droplets of water, but this is why it looks white because it's the same physics, it's mean scattering, as a matter of fact, driving that. If you look at it, I mean, it looks a bit blue, and that's the Rayleigh scattering part. It depends on the molecules, essentially. So we have actually, so far in LiquidO, already pioneered several different ways to do opaque scintillators, as a matter of fact. I would say, and this one, new ideas, I know some of them, in fact, some of them I don't know, maybe you haven't even learned, but there are 4 or 5 here that I cannot tell you because they're right now hidden, as a matter of fact, with LiquidO. But just to let you know that this is just exploding in many ways. So think about it, because maybe you have basically good ideas on that, and this is something that is looking very exciting. I'm not going to go to all the details, but yes, but oh, sorry. Microphone is not good? Okay. Is now better? Sorry, I didn't.
Okay, thanks, Anasfi.
Okay, thank you very much. Sorry about that. Okay, so in fact, I mean, this is one of the things that actually, in this context of opaque scintillation, our project that I'm going to tell you later on, that is called AntiMatterOTech, we've been funded by an extra €1 million, in fact, that is coming to Portugal, is coming to IST, precisely for exploring some of these opaque scintillators. And these, we're also in parallel basically working with LiquidO-based. This is the biggest constructor in the world of fibers, wave-shifting fibers, and we're basically developing stuff with them. So let me wrap up when it comes to LiquidO, let me bring a little bit to the potential of that. So with LiquidO, we have basically created points. So we have succeeded into our original goal, essentially to make points, and I'm gonna show you the data in 1 second, by the way. So we can basically get point-like basically topologies, and these would have basically information on the sub-millimeter basically level, up to the sub-millimeter level. This is the best you can get on the primitive level. You can actually get tracks, because a tracks is just a sequence of points, as a matter of fact. Very simple. I mean, that's how we're learning even in school. And that's, you will get even more precision if you have tracks, because you have correlated information about many points, so you actually have more information. This is like how you feed a straight line when you have many points, long story short. You can actually have complex, basically, combinations of points and tracks. I'm going to show you that before. So we have very, very nasty events. The question is, can we handle that? The answer is yes. Timing will become very important to be able to disentangle some of these possible degeneracies, but this is in principle. So long story short, I mean, LiquidO is a 5-dimensional, basically, system in terms of information that give you energy flow, kinematics, momentum, energy, PID, and so on and so forth. Of course, you need reconstruction to really look into that, and you need to optimize it to your favorite detector. So LiquidO is a collaboration that actually I created in 2016. We are about 100 people right now, and 11 countries, I mean, but about 20 institutions, and we've been working actually since 2016, and so that's what we are. But now let's go beyond LiquidO, because that was the framework. Let's now get it beyond its native composition. Imagine you scintillator, you have carbon and hydrogen. All you have in your detector, which is beautiful, by the way, but you want to go beyond. So for the radio purity aficionados that I know a few basically in the audience, I want to satisfy them. So liquid scintillators are, of course, one of the cleanest things we can build in the planet. Borexino has got to the 10 to the minus 20, and when I say this number, this is the moment you should make a minute of a pause, because that's scary. As a matter of fact, I mean, even myself, I don't realize how scary is scary, but it's scary. So you can make things on the 10 to the minus 14 relatively easily. Okay? You can go keep on going. The fibers are rather clean because it's a plastic. Plastics are rather good in terms of basically uranium, thorium, and this is 10 to the minus 12, but you also use less fibers than scintillators, so you actually reduce this number. There is no segmentation. This detector doesn't rely on pixelizing the detector because segmentation is dirty, typically. Dirty, very dirty, in terms of radioactivity, of course. Photodetectors would be at the end, we can put them farther, and silicon PMs are semiconductors as opposed to a metal that has basically a lot of radioactivity. Remember, photomultipliers are the reason why we have buffers, and we lose twice of the volume, I mean, sometimes just because of the buffer, because it's the only way basically to stop, I mean, the radioactivity of the photomultipliers, and there is no trick about it, I mean, to solve it. So removing the photomultipliers is a major success. Silicon is much better, semiconductors are much better. You can use the fibers actually to put them farther away. It would cost you some light, but this is, again, this is your physics. And then, can we dope it? Can we get physics beyond the hydrogen and carbon? And the answer is, depends on your physics, but the answer is yes. Well, first thing, nice, is that you don't care anymore about chemical stability. Shaw experiment, you may remember or may not, was about to measure theta 1,3. They would have discovered theta 1,3 essentially in the 90s, as a matter of fact. And you know why they didn't do it? Because their scintillator became green. They became LiquidO. Long story short, they screw up the scintillator because any LiquidO-like scintillator, you screw it up. Your detector was useless. But it turns out that you actually imagine, you solidify that, you can actually put your doping in suspension. Now it's a mechanical suspension as opposed to a chemical suspension. Chemicals are very difficult and sometimes very nasty because even by regulations you cannot actually use them in some cases. Depends if you're in a nuclear reactor, for example, you don't do it. If you're on the ground, maybe you don't do it either, and so on and so forth. So actually having the possibility of getting things in suspension, fantastic. You give it a spoon, cool it down very quickly, and let it basically hope is uniform. I'm joking on that, but it's just to give you a feeling of the potential. Now, let's try to dope these detectors with something else. Well, what people have been doing, so remember your detector is actually, from the purity, is actually very rich. You have basically carbon-12 to 99%, hydrogen to the rest, and everything that is carbon-12 is very small, and some impurities that you can clean up to the 10 to the minus 20 level if you want to do it a la Borexino. If you dope with things like cadmium, gadolinium, and lithium, you can actually do enhanced neutron captures. This is when you do just this, you do a pinch in your detector, okay? But now let's go nastier. Let's try to put a lot of lead, for example, in your detector, and you would be able to enhance basically interactions, charge current interactions that wouldn't be there, and neutral current interaction that wouldn't be there. And the cross-section is enormous. And because the cross-section is enormous, you can just by doping actually tune it and enhance interactions that you didn't have in carbon and hydrogen otherwise. And I'm giving you just the lead example, but you can look at the enjoy, by looking at basically the nuclear table, and you will see how much physics you have in there. And you can actually go even beyond. This is already basically on the 10% level or thereabout, but even you can go to the double beta level. I don't have to explain much because the snow plus basically is in the laboratory. But if you want to go to the ton level, you want to basically go play in a different game. And this is something that Cam Lansen is demonstrated, and snow plus is going to show, but you're deeper, and that's going to show it probably better. But nonetheless, cosmogenics are going to hit you very soon. And this is something we expect, although snow plus is deeper. And that is, of course, very, very, very good. Physics. Let me give you a little bit of appetite, and I kind of basically hopefully satisfy almost all of you, but maybe not everybody. The first thing, I come back to these electron, positron, and gammas in the MEV level, okay? Remember, in the MEV level, we are detecting 100 photons, okay? So this is really still, almost Poisson statistics. You can go a bit farther if you go to Juno, but this is typically the range. Typically, our detectors that cost even Juno, just built, a few hundred millions of euros, they don't make the difference between a gamma, a positron, and electron. Everything is washed out, okay? And it's washed out essentially into this kind of basically structure, sort of potato. But the reality is that you have this positron annihilation information, electron and gamma. And here the gammas, they go very far, but all that information is rather washed out basically in our detectors. In fact, electron, positron, and gamma doesn't even exist typically in our detectors. It's very, very, very tough. Everybody have tried, but you get very, very, very bad PIDs, long story short. If you're able to do that, and imagine you have a positron signal, for example, nuclear reactors, this is background, now you have basically reduced your backgrounds by probably 1, 2, or 3 orders of magnitude, I'm going to show you later. This means that you don't have to go so deep on the ground, as a matter of fact. And that is starting to solve the big problem that I was basically highlighting from the very beginnings. Now, let's imagine you go high in energy. This is a positron at 50 MeV. This is a Michel positron, you can consider it, or a Michel electron, as a matter of fact. this is what you get, but remember, when you get a muon stopping, this is what you get for free. And if you have a muon, and you see the sign that is a positron electron, you have the sign of the muon. If you have the sign of the muon, you can also have the sign of the pion, and the sign of the kaon, and so on and so forth. So you can track signs without any magnetic field, as a matter of fact. You can actually do directionality. I'm going to show it again. Even at these energies, which has very, very tiny energies compared to high energy events, you get basically directionality, tracking, and even you can measure the energy using range, as a matter of fact, which is complementary but related to essentially to the energy. If you keep on going high in energies, you can get interactions like the ones you would get in Dune, like 2 GeV, and you would get basically a pi minus into a mu minus into a Michel electron. Remember, Michel electron is not annihilating, so I know this is a minus, and that's exactly what we see. And this is a positron, and the positron is just doing an electromagnetic shower. And this little stuff that you see, this dust that you see in there, this is our MEV physics. As a matter of fact, this is the physics we do. Some people do physics with that, some people do physics with that. I mean, we're very happy with that, by the way, too. And this is a neutron that actually you can measure the time of flight. As a matter of fact, it's proton recoiling, and actually you measure the neutron, and then the neutron is going to capture, and you get the captions of the neutron. So you get neutrons beautifully, which is something very tough, for example, in liquid argon, as a matter of fact. So long story short, I mean, by actually looking at this kind of events, you can actually get tracking, sign tracking, and you can get a lot of information about time of flight, which give you even the energy of the neutrons, which would give you information about these interactions, actually the neutron, that is very important for the PID of the interaction and for the energy reconstruction of the neutron, of the neutrino. And you have an immense amount of information. You can dope it and start getting even farther, and calorimetric information is more. So this is the kind of event in dynamic, and you can see, look at a neutron. It's a mini neutrons, neutron, pack. And this time of flight, you would have done the time of flight very easily because the neutron is very slow. As a matter of fact, it's very, very easy to do time of flight of that in these kind of scenarios. So you see, in this interaction, there were about 10 neutrons that went out, and you would have no information about the energy reconstruction of the neutrino in this kind of interaction. Nonetheless, it looked like a very nice quasi-elastic-ish kind of event, and I think that basically the Dune people, please.
So each dot there is a photon.
Sorry, I didn't say that. Yes, absolutely. Yes, sorry about that. Sorry. I'm so used to it. And the color means how much charge it is. But imagine, for example, an event like that. Thank you for the question, by the way. I mean, imagine an event like that. If you, or maybe this one. For example, I love saying this. If you have an event of that type, you have an immense amount of information in terms of charge. But really, do you need the charge? Can you do a binary readout with just basically discriminators and just an event in black and white? And you would get an immense amount of information still. I mean, this energy, the energy, the little size, goes with the logarithm of the energy, as a matter of fact, the light bulb. It's like an electromagnetic calorimeter, as a matter of fact. So long story short, when you go to these kind of detectors, you don't need such a detailed readout, as a matter of fact. You may get away with some funky readout that is well optimized for that, just for the sake of the technology, because we're going to discuss it later on. And, but indeed, otherwise, there is an immense amount of information, and the question is, who pays for that? By the way, clearly this detector is over-designed. For this size of light bulb, there is too many fibers. I mean, this is arguable, but I'm not optimizing the detector yet. I'm just illustrating, the capabilities. Of course, when you make a detector and you have some money or you don't, then you stretch it. There you go. So this is just to emphasize that this information, I don't have the timing. Well, actually, you have the timing here. Within 1 nanosecond or 2, you already see a lot of information, and imagine your reconstruction flowing essentially in slides of time. It is so beautiful. As a matter of fact, this is how we recognize positrons and electrons and things like that, and gammas. But look at this, it's a proton decay. So the proton decay, where there is basically a pi zero basically on this side, and this is a positron. By the way, in CP violation, in Dune and hyper K, that's the signal and that's the background. And you can see how beautiful you can recognize the signal in the background. Pi zero contamination on electron positron is actually basically the main background, and you can see that you can measure it all with your finger. So long story short, even for CP violations, the power of that is just tremendous, as a matter of fact. And this is, of course, why Dune is going to do things of this type. Hyper K cannot. Hyper K cannot. But they play a different game. Right, let me show you some data, because I'm pushed in terms of timing. So this is data that we have already published, so you can look into the details of the publication. This is our detector. Actually, that was the old data. This is the new data that is going to be in a publication in hopefully a couple of weeks' time. And this is a detector that is about this size, essentially 20 centimeters tall, 10 centimeters across. And we can run it with water alone. So this is the beam spot. This is energy essentially going with 1/r², roughly speaking. It's in a transparent detector. And this is Cherenkov, and you can just basically see Cherenkov light cute, nice, very nice. You would expect this goes very forward. I mean, that is very forward, but remember that an electron at those energies, this is 1 MeV, is actually scattering a lot. The Larmor radius, no. The Mollier radius actually is very, very, very large. Okay, so this is basically our Cherenkov data, but now you can actually put the same detector with scintillator, a very bad scintillator, just lab, that is not a perfect scintillator, and you can see the Cherenkov there, basically there, and you can see if we scan in energy, you can see the energy threshold of the Cherenkov is actually there, so we're 100% sure the Cherenkov basically is being on and off. As a matter of fact, this is very cute. And remember again that this Cherenkov information is not using any topology because that's nice for a punch through particle, but it's very hard for an electron. Now let's put lab and PPO. So we now put another scintillator. You can see this is 1 over r squared. This is the little forwardness of the Cherenkov, and you can see 80 times more light essentially than Cherenkov. So this is why we do scintillators. We get almost 100 times more light. And you can get basically these beautiful profiles we can scan, and it's very hard now to see the Cherenkov, and this is something that you guys know very well. This is without, this small detector, of course, this is BPO alone. But nonetheless, it's very, very tough to see that. It depends on the concentration, as a matter of fact. But you can see something very, very bizarre happens here. The same scintillator, this basically red, once you cool it down, actually looks like that. It doesn't follow 1 over r squared. That's LiquidO. We are opacifying the light. What this says is that we are detecting more light at the very beginnings, so we are losing light at the very end. This is very simple, conservation of energy. If you measure the photons at the very beginnings, they cannot be basically later on. So the opacity of LiquidO is showing basically there. And in fact, this is what we see. This is LiquidO in blue, and this is transparent system. This is Cherenkov, lab plus PPO, and this is the new, with the new scintillator. And this is the same scintillator, warmer. This is the transparent-like, and this is cold. This is a mayonnaise-like, essentially, long story short. And we can measure basically the energy and the topology. So in fact, when we call LiquidO, we are basically seeing the lightness, a lot of light at the very beginnings, because the light ball is detected within a few centimeters. It's basically this big, as a matter of fact. Something that would have gone over 40 meters across, if it's basically detected within a finger, basically within your fingers. But of course, this implies opacity in the long distances. To show you more data, and this is all data, so this is basically LiquidO-like. This is a logarithmic scale, and this is basically transparent, so this is very flat behavior. This is 1 over r squared, and this is basically the light bulb. Most of the light is in the first few fibers. Most of the light, essentially, 60% if I remember correctly, okay? And if you actually ask your Monte Carlo how that would look like, well, this is basically what is happening in your transparent system. This is Gen 4, full Gen 4, and this is what is happening in the opacity, basically, system, and we can now basically look into the details of the simulation, and we can optimize if we have different opacities. This, what I showed there, I think is this plot, probably this one, but we think that we're more or less in between these levels. So we are making the light balls essentially within that level. So this is basically, a fraction of a millimeter, as a matter of fact, that we're basically making. But we're not trying to get, this is not a world record to get there. What you need is optimize your fiber pitch to your light bulb, basically to your light bulb, and try to maximize basically that. But you can make it as small as you can. As you want, I'm sorry. So, achievements so far. So, we actually have demonstrated the stochastic light confinement. I just show it to you. As a matter of fact, the paper is coming out. We can measure basically the light with no problem, any kind of light. We have measured, as a matter of fact, Cherenkov and scintillation, no problem whatsoever. We have measured in liquid and solid because actually we solidify the scintillator, as I showed that to you before. We actually can dope it because actually that is how we opacify the system, so we can dope it. And then, of course, we want to basically dope it with metals and so on and so forth. This is basically coming. And in principle, the opaque scintillation is actually working, the paradigm. So this is actually looking good. It's coming along very well, exactly as planned. PID now. This is the plot that we showed in our Nature paper, the first paper, where we show a gamma. And this was a very conservative Monte Carlo versus an electron. And just by doing that, you can see with a 90% efficiency, you can go 1 order, 2 orders, 3, up to 4 orders of magnitude, essentially, of PID, just saying this is point-like, this is not point-like. There is no funky reconstruction. We didn't try to do anything funky because we didn't want to show funky reconstruction. We want to show funky detector capabilities. Then if you put funky reconstruction, a funky detector, you go funky. That's super funky. I agree with that. Now, this is basically just to give you a feeling. This is what normal detectors would see. And normal detectors basically would wash down information. Oh, sorry, my animation is screwed up. There. This is the size of the light balls of the experiment. So we knew in the Monte Carlo, in this paper, we want to be very conservative. We show it much bigger. But we know the light balls basically are about 4 centimeters. So they are basically essentially the size of a patch, long story short. And this is basically the size balls, roughly speaking, adapted to the new data, and you can see the power of that is just going to be tremendous. So this plot is already old, and actually we will go even deeper on that, basically on that line. This is just to give you a feeling for the kind of basically degrees of freedom we're talking about. Now, can we do physics beyond that? But before that, let me wrap up what LiquidO is about. But LiquidO looks like a scintillator detector. You kind of think of that, well, this is kind of a la Juno, a la Snow Plasma, like that. It's not. It's not. LiquidO is another machine. It's a light detector, yes, but it's not working in the same way. In fact, this is basically my first attempt to summarize how LiquidO works. LiquidO works as a light TPC. Instead of drifting slow electrons, it's drifting light at the speed of light. That means the duty cycle is as high as you can possibly be. Of course, some neutrinos apparently can go even faster than the speed of light, but we don't talk about those anymore. But beyond that, I mean, this is basically a fast and powerful detector that can give information with very high duty cycle. It gives you calorimetry if you use scintillation, but even with Cherenkov, you actually have calorimetry too, depending on what you want. And you have time of flight information in any angle, as a matter of fact. This is why you saw this time of flight of the neutrons, as a matter of fact. So it's a time of flight system with a TPC with imaging capabilities, as a matter of fact, with ability to go to even to the KV physics by using scintillation. So it is a completely different type of animal, and very important, you can dope it. You cannot dope a TPC, a liquid argon TPC. If you dope a liquid argon TPC, instantaneously you would have troubles essentially for the drift of the electrons, as a matter of fact. If you dope liquid scintillators, you would have problems with transparency very quickly. So you can dope it, and hopefully you can dope it brutally, because that's the moment that basically things explode in terms of physics. I hope so, at least. Of course, doping a detector, don't take it as a grant. I mean, yes, it's as nice as putting salt in the soup, but that's an art. Whenever you dope any element in a certain scintillator, that's a universe in itself. And you would see just doping tellurium in a scintillator is probably 10 years of R&D and probably, I don't know, 10 million-ish thereabout, if you consider personnel and so on, of effort. So I don't mean to underestimate, this is a very strong point, but at the same time, there's a lot of work behind that. But the potential is there. Right, physics, because that's what we're here for in many ways. Let me go to physics. So it turns out, basically, that we can, why did it go so fast there? No, it goes actually good. So it turns out that actually we have basically one facility, a show, essentially, where we have basically a very nice antimatter, essentially, generator, which is the show nuclear reactors. Okay, this looks a little bit like the Lord of the Rings, as a matter of fact. And here, down here, there is a former nuclear reactor that is called show A that used to run in the 50s during the Cold War, as a matter of fact. And in fact, it turns out, the reason why I'm bringing this up is because that nuclear reactor, the show A nuclear reactor, is being dismantled as we speak right now. This is actually something of the size of Super Kamiokande. I'm not kidding. 50,000 meters cube of volume, close to one of the most powerful nuclear reactors in the planet. So you have a Super Kamiokande-like cavern, close to one of the most powerful nuclear reactors in the planet. Oh, that's celestial. That's celestial. And this is exactly what we're exploring, and this is what we call super show. Okay? So the idea is to use, we don't need even all of it, we only need this cavern, and EDF, and this is the wall upside down, is asking us, do you want to take it? The keys are on the table. Do you want to take it? Yes, exactly. That's exactly my reaction when they said it. And well, I kind of suggested it too. But anyway, but it's crazy. Normally, this facility, this is about €500 million if you have to build it from zero. Okay? This is what it costs. It would cost. But it would cost much, much less if we recycle it, especially from a nuclear reactor. And basically, this is actually happening. And before we do that, we need to validate. There is one little problem with that cavern. This is beautiful, but it's basically barely 100 meters underground, which means we're very close to surface. Oh yes, there has to be a caveat there. If we have the technology to do that, then you can get away with such a low overburden. And that's in fact what we call the super show. And this was presented at CERN in November 2022. This is a possibility. I'm not saying that this is there in no way, but this is something that we're exploring, but this is giving you an appetizer of the kind of thing we want to do. So this is the potential of the site, would be a detector of the size of NOVA, 10 kiloton, LiquidO, it has to be, and we would need 2 little ultra-near detectors that are going to be used to monitor the nuclear reactor. This would give you the best measurement of theta 1 3, theta 1, 2 will measure solar and reactor neutrinos, as a matter of fact, providing we can do LiquidO with Raghaban's original idea about measuring solar neutrinos at low energies. And this project down here to have a detector there is already happening. In fact, since December 2022, this is the project that we're building right now. Is actually the demonstrator project for SuperShow. It's actually for other purposes, but it turns out actually it was born basically, as a matter of fact, I was thinking of SuperShow when basically we thought about that, but it turned out actually that this is actually a project actually done by the EIC for reactor monitoring. This is exploring the possibility, can we now provide neutrino information as a reactor tool for instrumentation? And this is something that it has been dreamt for a long time, but now with the power of LiquidO, we can go to another level. So the potential maybe is to make a new detector there. This is still very remote, but just to give you an appetizer, stealing from NOVA, actually, this is a beautiful diagram of NOVA. It turns out that all the dimensions are like NOVA, and if you think about NOVA, it's just LiquidO with segmentation in many ways. So actually we simplified in many ways and we can increase the light level. It's relatively, in principle, very easy, okay? There is a new collaboration basically behind that. We call it Cloud from the particle physics point of view, and there is AntiMatterOTech. This is the original project essentially for essentially reactor monitoring, as a matter of fact. And the idea basically is to place this first detector, 5 tons to 10 tons, essentially almost on surface, close to the nuclear reactor, and to be able to measure on the level of thousands, tens of thousands of neutrinos per day, okay? So the location essentially is going to be at the foot, essentially, of the nuclear reactor. It's the first time EDF allows these people, crazy scientists, essentially, to be there. They never allowed, basically, us to be there. And the show detector was here, double show was here, double show was there, matter of fact, so we never actually dreamt to be there. And we're gonna be located basically there, and that would allow basically to see even inside the nuclear reactor. And that's one of the nice things. So we're going to do innovation, nuclear reactor basically innovation, instrumentation innovation, and fundamental physics at the same time. That's exactly the point. The side, the particle physics side, we call it Cloud. The instrumentation basically of nuclear reactor, we call it AntiMatter. And it turns out, it's a demonstrator of SuperShow. If it doesn't work, SuperShow cannot work. But if it works, maybe SuperShow is basically on its way. Let me just give you an appetizer, just in case you haven't seen neutrinos in a nuclear reactor, because to me, this is one of the most beautiful plots we did in double show. What you're going to see here is the number of neutrinos versus the power of the nuclear reactor from the web. And what you're going to see is when we switch off the nuclear reactor, this is just the spectra basically, which is the cross section times the flux. But once we switch off the nuclear reactor, you can see how our neutrinos basically disappear. And this is not fitted. We're not fitting the neutrino data to the actual profile of the power. This is absolutely independent. This is just an illustration. And this is just a little bit of a slide. There is no background because it has been subtracted. You would see something here. This is actually reactor off, but you would see, I'll bring it back to you in 1 second. This is now when it switches on, and you can see how reactors and neutrinos just follow one another. It's just scary. So I told EDF when they saw that for the first time, they got impressed. I told them, we're watching you guys. I mean, watch out what you do. And that jokes apart, I mean, in many ways. But what is very interesting, is this reactor off data that you see here. This reactor is not only coming from the reactor, but it's also coming from the pool, because there is a lot of fuel basically there. And there are certain places where they don't have nuclear reactors anymore, but they have pools. One of them is called Fukushima. And nobody knows how much reactor power, how this stuff is. And this is something that we're also exploring. If we demonstrated that we're able to monitor the reactor off and even the pool with that signal to background, this means that we're making instruments even to help in situations of Fukushima-like or Chernobyl-like or anything like that. So we're making tools, we don't know how far they can go, that may help basically society in other ways. So that's actually one of the things of AntiMatterOTech. This is to me the long range of AntiMatterOTech, but it's not such a long. I was in Japan last year negotiating with the EDF Japan and trying to see whether we can start basically understanding whether there is a route to talk to a Fukushima eventually. And this is in fact the project that we're going to bring to here. So this project is funded, preparing the construction. In fact, we want to build it here, in fact in Lisbon, and I can tell you a few words on that if you have questions. And we want to expose it to reactors, solar neutrinos, on surface, and that's the scary thing, if we manage. And this implies that you can also do supernova, but atmospheric neutrinos and many other things. And let me close basically there. Oh, just to emphasize, this technology, this detector SuperShow, turns out to be almost identical in size to one of the far detector basically of Dune. So it turns out that everything that we're doing, if it doesn't happen to work for SuperShow, it It may turn out to work for Stu, it may turn out to work for something else. We would see later on. I mean, this is, of course, early exploration, but that's basically the potential things that we can think of LiquidO. So I'm not going to basically go over that, but the big thing is that LiquidO seems to be working, and we want to try to bring physics to surface and beyond, hopefully, and hopefully do even more physics that we can and remove this technological barrier beyond a lot of neutrino physics and go for more. Thank you.